Hi, welcome to What About g-2 of the electron and tau? So you might have heard about the recent measurement of g-2 of the muon. Now the muon is one of the particles of the Standard Model. The Standard Model has 6 quarks, 6 leptons, gauge bosons, and the Higgs boson. The muon is a charged lepton. But the Standard Model also has 2 other charged leptons, the electron and the tau. So if we're interested in muon g-2, you might be wondering, are we also interested in g-2 of the electron and the tau? And the answer is yes. And in fact, there are measurements of g-2 of the electron and g-2 of the tau. So here we'll talk about their relative status and importance, and why muon g-2 is the most interesting of the 3 to look for physics beyond the Standard Model right now. Okay, so here we give the current status of g-2 for the electron, the muon, and the tau. In the left-hand column of numbers, we have the Standard Model prediction, and in the right-hand column, we have the experimentally measured number. Usually these numbers are quoted as the quantity called A, which is just g-2 divided by 2. So for example, A mu is just g-2 of the muon divided by 2. I will use both terms in this video, so just know that they are equivalent up to a factor of 2. Okay, so for each of the numbers given in the table, its uncertainty is given in parentheses and applies to the last digits of the result. Okay, so in the middle row, we have the result that made recent headlines. This is A mu, the result for the muon. The difference between the measured result and the Standard Model prediction stands at 4.2 sigma. In the top line, we have AE, the result for the electron. Both its measured value and its value predicted in the Standard Model are much more precisely known than those of the muon. We can see that the results have more significant digits than the muon results. And lastly, we have the results for A tau. The measured value, shown in the right-hand column, has a very large uncertainty. Experimentally, very little is known about g-2 of the tau. Okay, so here are the references from which the numbers on the previous slide were taken. For the electron, muon, and tau, I've listed the paper that gives the value predicted by the Standard Model and the paper which gives the strongest experimental measurement. So this might lead us to ask the following questions. Why are we paying more attention to muon g-2 than we are to E and tau g-2? Now in the case of tau g-2, it's because the experimental precision is not so great. But then we can ask, why is tau g-2 so poorly known? And in the case of electron g-2, since electron g-2 is so precisely known, why aren't we focused on that instead of muon g-2? Okay, so let's start with the first question. Why is the error bar on tau g-2 so large? So in the case of electron and muon g-2, the basic experimental idea is that you place the lepton in a magnetic field, and you observe how its spin interacts with the magnetic field. Although I should note that the experimental methods for the E and the mu are actually very different from each other. However, in the case of the tau has a very short lifetime, and so it decays before you can make any of those observations. So to put that in perspective, let's look at the lifetimes of the electron, muon, and tau. So the electron is stable. As far as we know, its lifetime is infinite. The muon has a lifetime of 2.2 microseconds. Now, that might sound short, but it's long enough to do one of these measurements. However, the tau has a lifetime that's 7 orders of magnitude shorter than that of the muon. So good luck with that. So in order to measure g-2 of the tau, we need a fundamentally different idea. So g-2 of the tau is related to how the tau spin interacts with an applied electromagnetic field. From the particle physics perspective, that means that g-2 of the tau is also related to how the tau interacts with the photon, which we call gamma. And this means that you can possibly look at g-2 of the tau in collider experiments. So currently, the best result for g-2 of the tau is from the Delphi experiment from 2004. Delphi was one of the 4 experiments at LEP, which ran between 1989 and 2000, and LEP was the Large Electron-Positron Collider, and it was located in the tunnel where the Large Hadron Collider is now. Okay, so here's the process that Delphi looked at. They looked at E plus E minus colliding to make E plus E minus tau plus tau minus. So basically what's going on in this diagram is that you have an electron and a positron coming in from the left-hand side of the page. Each of them radiates a photon, and then those 2 photons collide to make a tau plus tau minus pair. Now the tau magnetic moment, and therefore g-2 of the tau, has a small effect on these vertices where a photon interacts with a tau. This means that if you can measure the process E plus E minus goes to E plus E minus tau plus tau minus, you can, in principle, measure g-2 of the tau. Now, while this works in principle, the sensitivity, unfortunately, isn't great. So the result they got was that the experimental value of A tau was minus 0.018 plus or minus 0.017. Now, the standard model prediction is 0.001 and some more digits. So this result can't even see the standard model prediction, let alone new physics contributions. Okay, so that's the story about tau g-2. Now let's move on to electron g-2. So our next question is, if electron g-2 is more precisely known, why are we so interested in muon g-2? Okay, so let's start by looking at the relative precisions of electron, muon, and tau g-2. The experimental results and the standard model prediction are usually written in terms of A, which I'll remind you is just equal to g-2 divided by 2. Okay, so here's the same table we saw at the beginning of the video. To look for signs of new physics, we care about the difference between the value predicted by the standard model and the experimentally measured value. But here, to compare the precisions of the different results, we're interested in the uncertainty on this difference. To get this, we take the uncertainties on the prediction and on the experimental value and add them in quadrature. This means that we square each of the uncertainties, add them, and take the square root of the result. We'll call each of these resulting uncertainties sigma. So let's say we're interested in the difference between the predicted value and the measured result for AE. To get the uncertainty on that number, which we call sigma E, we take the uncertainty on the standard model prediction, which is 2.3 times 10 to the minus 13, which is the number shown in parentheses, and add that in quadrature with the experimental uncertainty, which is 2.8 times 10 to the minus 13, which is the other number in parentheses. And then this gives the uncertainty on the difference between the prediction and the measured result. we get that sigma E equals 3.6 times 10 to the minus 13. And similarly, for sigma mu, we get 5.9 times 10 to the minus 10. And for sigma tau, we get 0.017. Okay, so here are those uncertainties, sigma E, sigma mu, and sigma tau, that we got on the previous slide. So let's compare them. So the difference between sigma E and sigma mu is a factor of 1600. So basically sigma mu is 1600 times as large as sigma E. And sigma tau is 30 million times larger than sigma mu. So this means a couple of things. This means that electron g-2 experiments are so precise that they can see deviations from the standard model prediction that are only 1/1600th the size of those that would be visible in Muon g-2 experiments. Experiments that measure g-2 of the muon, in turn, can see deviations from the standard model prediction that are 1/30 millionth as large as those that would be visible in experiments measuring g-2 of the tau. This is both a statement about the precision of Muon g-2 experiments and a statement about the lack of precision on the measurement of g-2 of the tau. New physics effects would have to be utterly gigantic in order to be seen in a measurement of g-2 of the tau. Okay, so at first glance, the electron might seem like the best of the three to look for signs of new physics. But now let's see why that isn't necessarily the case. Okay, so let's imagine that some unknown type of new physics exists. And let's say that it contributes to A for each of the three leptons. So it contributes to AE, A mu, and A tau. And let's call those new physics contributions A sub the lepton NP, where NP stands for new physics. So for each lepton, A, so AE or A mu or A tau, is a sum of the standard model contribution and the new physics contribution. Okay, so we have our expressions for AE, A mu, and A tau, and they each consist of a standard model term and a new physics contribution. Now, if the three new physics contributions are all equal, so if AE NP and A mu NP and A tau NP are all equal, then the electron experiments that measure AE very precisely are the place to look. But instead, what typically happens in new physics scenarios is that the new physics contribution to AE is much smaller than the new physics contribution to A mu, and the new physics contribution to A mu in turn is much smaller than the new physics contribution to A tau. So the situation is a bit complicated. Now, in most scenarios of new physics, not all, but most, g-2 gets contributions from new particles in loop diagrams. So here's an example one-loop Feynman diagram that comes into the calculation of A mu in the standard model. If you have new physics contributions to A mu, you can also get new diagrams that contain particles that are not part of the standard model. Now let's say that the new particles have a mass that we're going to call m sub np. And we're going to assume that m and p is large. So the mass of these new particles is much larger than the masses of the electron, the muon, and the tau. Now, for a lepton L, where L is the electron, the muon, or the tau, the main new physics contribution to A sub L, which we were calling A sub L and P, is typically proportional to the mass of that lepton squared divided by the mass of the new particles squared. And so this means that the contribution to AE from new physics would be expected to be proportional to the mass of the electron squared over the mass of the new particles squared. The contribution to A mu from new physics would be expected to be proportional to the muon mass squared over the new physics mass squared. And the contribution from new physics to A tau would be expected to be proportional to the mass of the tau squared divided by the mass of the new particles squared. Okay, so to understand why that's important, let's take a look at the values of the lepton masses. So the electron has a mass of 511 keV over c squared. The muon has a mass of 106 MeV over c squared. And the tau has a mass of 1.78 GeV over c squared. And this means that the muon has a mass approximately 207 times that of the electron. And the tau has a mass approximately 16.8 times that of the muon. Okay, so let's look back at those expected relative sizes of the new physics contributions to AE, A mu, and A tau. So we said that the muon weighs about 207 times the mass of the electron. And we can see that the new physics contribution to A mu is expected to be proportional to m mu squared. And the new physics contribution to AE is expected to be proportional to me squared. This means that we would expect the new physics contribution to A mu to be 207 squared times as large as the new physics contribution to AE. And 207 squared is about 43,000. So basically this means that typically we would expect the new physics contributions to A mu to be about 43,000 times as large as the new physics contributions to AE. Similarly, because the tau weighs about 16.8 times the mass of the muon, we would expect the new physics contributions to A tau to be about 16.8 squared, or 280, times the new physics contributions to A mu. Okay, so now we're finally ready to answer the question, why muon g-2 and not electron, or for that matter tau g-2? So we saw that from the precision of the electron and muon g-2 experiments, that the electron g-2 experiments were sensitive to new physics that was 1/1600th the size of that which would be visible in muon g-2 experiments. However, unfortunately, we also saw that the effects of new physics in electron g-2 are only expected to be of order 1/43,000th as large as the effects of new physics in muon g-2. So, muon g-2 wins out. While we're at it, let's also compare muon g-2 to tau g-2. So we did see that the effects of new physics in g-2 of the tau were expected to be of order 280 times larger than the effects of new physics in g-2 of the muon. However, unfortunately, due to the lack of the precision in the measurement of g-2 of the tau, the new physics effects in g-2 of the tau would have to be 30 million times as large as the new physics effects in g-2 of the muon in order for them to be visible in g-2 of the tau and not visible in g-2 of the muon. And so g-2 of the muon wins again. So the short version of the story on g-2 of the electron, muon, and tau is the following. For the electron, g-2 is very well known, but the new physics contributions are expected to be tiny. In the case of the tau, the new physics contributions are expected to be large, but unfortunately we have huge experimental error bars. And in the case of the muon, well, that's the sweet spot. So right now, muon g-2 is the most promising of the three to look for new physics. Now, we should note that this is only what is typical for new physics contributions, and there could be exceptions. So for example, what if we consider a new physics scenario where new particles only interact with the electron or with the tau? g-2 of the muon might not be so useful in such a case. Okay, so let's briefly summarize. So here we looked at the relative utility of the measurements of g-2 in the electron, the muon, and the tau, given reasonable assumptions about the behavior of new physics effects and the current experimental precision. Measurements of g-2 of the electron are extremely precise, but unfortunately, new physics effects in it are expected to be tiny. On the other hand, measurements of tau g-2 are currently too imprecise to be useful. So currently, g-2 of the muon is the most promising of the three.